This video is a review of SI units, dimensional analysis, and unit conversion. We'll also cover the topics of position, displacement, and distance. We're going to begin by talking about SI units. When we talk about the position, the displacement, or the distance that an object travels, we're going to be using meters as our SI unit. This may seem obvious, but it's important to keep in mind that we're not going to be using the imperial system. The imperial system typically includes inches, feet, miles, some of the units with which we're more familiar in the States. Most of the rest of the world actually makes use of SI units, and we in physics will as well. That's not to say that there won't be times that you may in fact have to convert from imperial units to SI units and vice versa. When we discuss mass, our base unit is the kilogram. The abbreviation is kg. For time, our base unit is the second. And we just abbreviate it with a small s. These are not the only base SI units that exist. For example, Kelvin is used when talking about temperature, and amperes are used when talking about electric current, but we won't get there just yet. On the left side, you'll see a sheet of unit conversions. I'm only going to require that you know the prefixes giga through pico by heart. All other ones I would give to you on an exam. You should familiarize yourself with these types of conversions. That being said, it's much easier to remember how many nanometers are in a meter and how many meters are in a megameter than to memorize how many nanometers are in a megameter. So oftentimes it's easiest to break it down to its base unit before you convert. Let's say, for example, that a cat walks 3 kilometers from Studio City to Van Nuys, and I ask you how many centimeters has this cat walked. It's much easier to go from kilometers to meters and then from meters to centimeters than to go straight from kilometers to centimeters. Our conversions will become much more complicated, so it's worth learning this approach first. Hopefully this is familiar. So again, as shown in class, I begin with what I've already been given, that I have 3 kilometers. I multiply it by some sort of ratio that will be equal to 1, but will allow me to cancel out my kilometers and just leave me with meters. In order to do so, I have to be sure that kilometers are the units that I use in my denominator and meters are in my numerator. So now the question is, how many meters are there in a kilometer? Should I have 1,000 on top and 1 on the bottom, or vice versa? The answer is that I should have 1,000 on top and 1 on the bottom, because I have 1,000 meters in 1 kilometer. So basically all that I've done is I've multiplied by 1. I need to multiply by some ratio that won't actually change the value of this 3 kilometers, but will allow me to convert from kilometers to meters. So in doing so, I can cancel out my kilometers, and my answer is 3,000 meters. 3 kilometers equals 3,000 meters. I must be sure that I convert my units from meters to centimeters. Now I know how many meters I have, but the question is asked for how many centimeters the cat has walked. Okay. So now I know that there are 100 centimeters in 1 meter. I determined that the cat has walked 3,000 meters. So again, I must multiply this by some ratio that will allow me to convert to centimeters from meters. Meters will go on the bottom, centimeters on the top, because I want to cancel out my value for the meters. 100 centimeters in 1 meter. And I find that the cat has walked a total of 300,000 centimeters. Now I did this in steps, but I could theoretically have done it all in one go as well. I could have begun with what I was given, 3 kilometers, multiplied that by something that would allow me to get rid of those kilometers. It's the first ratio that you saw. This allows me to cancel out my kilometers, and then I can multiply this also by 100 centimeters over 1 meter, which allows me to cross out the meters. Alright, so now I'm going to multiply 3 by 1,000 by 100. I get my same exact value as before. The cat has walked 300,000 centimeters. Now I want to discuss slightly more complex unit conversions, particularly those that involve distance and time. A cheetah at top speed can run 75 miles per hour. We want to find out how many feet per second it can run and also how many meters per second it can run. So these are some of the abbreviations that we use. FT for feet, M for meters. MPH is often used for miles per hour. But in this case I wanted to be explicit because we have an M over here for meters, and then this would also be an M for miles. So let's start off with what we've been given. 75 miles per hour. There are actually a couple of conversions that need to go on here. So we have something in distance and we have something in time. We need to get our hours to become seconds and our miles to become feet. So fortunately, when we're going from miles to feet, we're not having to change between SI units and imperial, so that should make our lives a little bit easier. So now I'm going to multiply that by something so that I can get seconds on the bottom, because that's what I'm going for. Some way to get rid of my hours. In order to do so, I have to say that 1 hour is equal to 3,600 seconds. And that's because there are 60 seconds in a minute and then 60 minutes an hour. So I just multiplied 60 by 60 and got 3,600. So that takes care of my time. Now I need to be able to change my miles to feet. I put miles in the bottom because that's what I don't want anymore. I put feet up top because that's what I'm looking for. In 1 mile, there are 5,280 feet. I can cross out my miles. I multiply all the values in the numerator, all the values in the denominator. I find that this cheetah can run 396,000 feet in 3,600 seconds. And of course I can't just leave it like this. I have to divide so that I only have one value in feet per seconds. A cheetah can run 110 feet per second. Remarkable. Okay, so now we can convert that into meters per second and address the second question here. Okay, I begin with 110 feet per second. Maybe to make this clear, I'll just do it like this. 110 feet in 1 second. You can write it either way. Okay, and now I want it to be in meters. I don't need to do any kind of time conversion because it's already in seconds. I'm just going to find some way to get rid of my feet, convert it into meters. So the question now is, how many feet are there in a meter? Okay. There are 3.3 feet in 1 meter. I'm actually just going to erase this seconds. It should only say S. Okay, if you put SEC, that's not a problem necessarily, but it is good to be consistent with your units. Okay, I can cancel out my feet. I find that the cheetah can run 33.3 approximately meters per second. These kinds of unit conversions become relevant when we start off talking about one-dimensional kinematics. Just to review the concept of position, we have two categories, two concepts that fall under the idea of position or a change in position. The first being displacement. Now remember that displacement itself is a vector, which means that it has both magnitude and a direction. Distance, on the other hand, is a scalar. It only has magnitude. In position, we can use delta x, delta meaning change. We could use delta d, distance, or delta s. Sometimes people like to use delta s, it's a change in the state of position. I tend to prefer these two. I swap back and forth. The full equation for the change in position would be that our delta x is equal to our final position minus our initial position. Okay? You can also, instead of using I for initial, you could also use O. Either way. Those both refer to an initial state. For the final, though, we almost exclusively use F. Likewise, I could have written delta D is equal to D final minus D initial, or D naught. Okay, let's examine a problem that has a man running from points A to point F, passing through points B, C, D, and E en route. So the two questions are, what is the distance that he's traveled, and also what is the displacement? Okay, so keep in mind that the distance here is our scalar. Our displacement, on the other hand, is our vector. So for the displacement, it is going to matter the direction. So we're actually going to tackle that question after. Let's assume that each block is worth 0.5 kilometers. So we need to calculate how many blocks over he's going to be walking. So from point A to point B, he's walking 6 blocks. B to C, he's walking 2. C to D, 3. D to E, 1. And E to F, 1. So he's walking a total of 13 blocks. Okay, 13 blocks at 0.5 kilometers each. He has run a total of 6.5 kilometers, and that's his distance. For the displacement, we're only concerning ourselves with where we began and where we ended up. We don't care about the journey. So we began at A, and we ended at F. Okay, so this here is going to be the magnitude of our displacement. We have moved over to the right 4 boxes and up 3. So think about how it is that you might be able to calculate this distance. We know here that this is going to create a right angle here. We can envision this almost as being a triangle itself. Because he could have accomplished the exact same task by just moving over 4 boxes to the right and 3 boxes up. So if we use the Pythagorean theorem, we can figure out the magnitude of this displacement here. I want to be sure that you're familiar with the Pythagorean theorem. I'm sure it's something you've been introduced to before. That a squared plus b squared is equal to c squared. And we can determine whatever this c squared is by taking the square root of a squared plus b squared. Okay, so let's figure out what our a's and our b's are. In walking 4 boxes to the right, he has walked 2 kilometers. I'm going to plug that in as my a and square that value and add that to 1.5 kilometers, which is the distance that he has traveled north. I'm going to set that equation equal to c. C is equal to 2.5 kilometers. But now, of course, we have to concern ourselves with the direction. So let's define all motion to the right as being east, all motion upward being north, all to the left being west, and all down being south. Now, if you do happen to remember the angles for a 3, 4, 5 Pythagorean triangle, you might remember that the smallest angle should be equal to 36.9 degrees. Okay, so I could say that this person has walked 2.5 kilometers at 36.9 degrees north of east. Okay, it's north of east because it's above the horizontal axis in the easterly direction. What's important is that for displacement you include both a magnitude and a direction because it's a vector, not a scalar.